In this problem, we have a parallel plate capacitor as shown in the picture. Half of the gap between the plates is filled with plexiglass and the other half is filled with air. The parallel plate capacitor is connected to a battery of known voltage, which is 26 volts. And the shape of each plate is a square of known side, which is 15 centimeters. The plate separation is also given 3.2 millimeters. We'd like to calculate the energy stored in this capacitor. Because we know the voltage and the physical properties of the capacitor, it makes sense to use this formula, U equals CV squared divided by 2, to calculate the energy stored in the capacitor. So V is given the voltage across the plates of the capacitor. What is C on the other hand? We need to calculate C, right? The plate area we can calculate. We know each plate has a square shape with a given side and the plate separation is given. Now we'll just use the formula for C, but it turns out half of the capacitor is filled with plexiglass and the other half is filled with air. In this case, how do we apply the capacitance formula? Now if you think about it, we can model this capacitor as the combination of two capacitors connected in parallel. So if you think about it, when two capacitors are connected in parallel, what do they look like? So they will be connected like this. The positively charged plates will be on the same side and connected. On the other hand, the negatively charged plates will be on the other side of the gap, and connected together. So from the picture, you may be tempted to think that this is a series connection, but it's not, and it's a parallel connection. Because if you think about it, a series connection for two capacitors would look like this. So positive plate connected to the negative plate of the other capacitor. So there's a alternating positive and negative plates would be the series connection, like so. So here's my battery basically. But this is not what we have. Instead, we have the parallel sides, the positive sides connected together and the negative sides connected together on the other side. So this is really a parallel, equivalent to a parallel connection of two capacitors, one filled with plexiglass and the other one filled with air. So really what we need to do, and this is my battery, so what we need to do is to calculate the equivalent capacitance for these parallel capacitors, parallelly connected capacitors. So we can call the plexiglass capacitor C1, for instance, and the air-filled capacitor C2, and combine C1 and C2 to find the equivalent capacitance. So I'm going to modify my formula here a little bit and make this equivalent capacitance, like C equivalent instead of just C equivalent here. Now let's quickly remember the capacitance formula in general. How do we calculate capacitance given the physical properties of a parallel plate capacitor? C is equal to dielectric constant K times epsilon 0 times the plate area, capital A, divided by the plate separation D. So we're going to apply this formula to C1 and C2 to find the equivalent capacitance eventually. Let's also remember the rule for equivalent capacitance calculation if two capacitors are connected in parallel. For parallel connection, we simply add the two capacitance values. So then C equivalent is equal to C1 plus C2. Let's continue this calculation here. Energy stored in the capacitor, capital U, is then equal to C1 plus C2 times V squared divided by 2. Now let's rewrite this formula and substitute the expressions for C1 and C2. So we have V squared over 2, and in parentheses for C1, I'm going to put kappa sub P for the dielectric constant for plexiglass times epsilon 0 times the plate area. Now what is the plate area equal to? Remember, the original plate area is simply L squared because we have square plates. Now the plates are cut in half, and C1 and C2, each one will have half of that plate area. So then the plate area for each sub-capacitor, let's say, will be L squared divided by 2. So maybe let me put the plate separation here in the denominator, and the plate area will be L squared divided by 2. And this is valid for each of the capacitors C1 and C2. So this is C1, the plexiglass filled capacitor, plus the air filled capacitor C2. What is the dielectric constant for air? That's just 1, so I'm going to omit a kappa here. I'll just start with epsilon 0 divided by d, plate separation, times the plate area, again half of the square plate area, L squared divided by 2. Next, let's rearrange this expression. Let's simplify it a little bit. We have a lot of common terms. Let's factor them out. So what is common? We have V squared. That's already outside of the parentheses. And then inside the parentheses we have epsilon 0, capital L squared, divided by 2 times d. Well, we have another factor of 2 actually coming from L squared over 2. So combining that factor of 2 with the one that is already outside of the parentheses, that's a factor of 4 times plate separation d. And inside the parentheses, what do we have left? We have kappa sub P, dielectric constant for plexiglass, plus 1. Now let's go ahead and substitute the numerical values to calculate the energy stored in the capacitor numerically. For epsilon 0, I'm using 3 significant figures, 8.85 times 10 to the negative 12 farad per meters. And for dielectric constant for plexiglass, I'm using 3.4, which is the value in the textbook that I'm using. And when we calculate the energy numerically, we get 4.6 times 10 to the negative 8 joules. Here's a nice follow-up question. What happens to the energy stored in the capacitor if we remove the plexiglass while the battery is still connected? So we're not changing anything in the setup. The only thing that we're doing is to remove the plexiglass from the left-hand side. Basically, this is gone. Now, what happens to C1? C1 will be also filled with air, so the two capacitors will be basically identical. How can we modify our calculations to figure out the value of the energy stored in the capacitor now? Let's take a look at our previous calculations. Now that the plexiglass is gone and the first capacitor, or C1, is also filled with air, in our calculations we should use 1 instead of kappa sub P for C1, just like we did for C2, like so. So let me also remove 3.4 from my numerical calculation. So I'll just put 1 here. The two capacitors are now identical. And if we redo the calculation, we get 2.1 times 10 to the negative 8 joules for the energy stored in the capacitor. Now this is less than the value we calculated earlier. Does this make sense? It does make sense because when we remove the plexiglass, the overall capacitance value for the capacitor decreases, meaning the ability of the capacitor to store energy decreases. Hence, the value of the stored energy is less than before with the removal of the plexiglass material. Of course, that is for the given fixed value of the applied voltage between the terminals of the capacitor.